Swayam Prabha. Digital India. Educated India.
So far we have discussed about basically using vibration monitoring as a tool for finding out the health condition of machines, and then we saw how wear debris analysis or oil contaminants analysis could be used to pinpoint the fault in machines. Now in this class and so on, we will be discussing about the other techniques of condition monitoring, which constitute towards the 10% of the monitoring methods throughout the industry in the world. And especially motor current signature analysis has come up as a very emerging technology in condition based maintenance, and we at IIT Kharagpur have contributed a lot to it through our research over the last decade. And in fact, in this class and the subsequent class, I will be also presenting some results from our research at IIT Kharagpur. And before I spend or discuss on motor current signature analysis, I would like to in this class talk about how do we find out the defects in electrical motors. As you know, 90% of the cases in systems in machines, the driving unit is an electrical motor. So, a fault in an electrical motor is of paramount importance. So, it has to be detected beforehand, so that we do not have an unnecessary downtime. Along with motors, I will be discussing about transformers as well. So, well, if I was to classify the electrical machines, there could be many different types of electrical machines. By machines, I essentially mean a motor or a generator. Particularly, if you go to the steam power plants or the hydropower plants, you will see large generators, and typical capacity large type of generators would be around 660 megawatts, hydel generators would be about 313 megawatt and so on. And of course, if you go to the plants, large rolling mills etc., we will be having large induction motor or synchronous motor of the around of 10 megawatts in power. And then we have the AC commutator motor around 900 kilowatt, and invariably in many plants and steel plants, paper mills, cement plants, you will see these kind of motors are used, and this is the single most prime mover in their plant. For example, just to begin with, if I give you an example of a cement plant, essentially we have a motor through a coupling, it drives a gear box, and then actually to this gear there is actually a large kiln. I am drawing it in series, but actually it is meshed with the gearbox. This is the rotary kiln, which rotates approximately about 2 to 3 rpm. Okay, but it could be carrying loads of several tons, maybe 10 to 20 tons of material. The idea, as you know, in a cement plant, all the mix is added, there is a feeding device here, and then it is turned with a hard grinding media, and then you will have the powder cement coming out. But our focus is, we know how to find out the faults in cracks in the kiln, which is a common type of failure in the kilns. Failures in the gearboxes or the couplings are known to us. Through vibration monitoring we can do that. But my focus here is on what happens if this motor is at fault. Okay. How do you find out a fault condition in the motor? Okay. Because if the motor shuts down, your plant is shut, isn't it? So, let us see, and this is the case of a cement plant. Same is true in rolling mills, paper mills, conveyor drives, the powering unit are these motors. Okay. So, motors are usually an AC commutator motor, typically 900 kilowatt in power. Of course, there are larger motors we could be using, and they all are almost designed to run at constant speed. And this gearbox, because from a RPM of 1440 RPM, you are finally rotating the kiln at 2 to 3 RPM. So, you can imagine the amount of speed reduction which is being brought about the gearbox. So, this is a heavy gearbox, multi-stage gearbox and so on. Now, realizing the importance of fault detection in motors, we will see what are the possible different types of faults which can occur in an electrical motor. Of course, before that, again we have the DC machines. DC machines, particularly in your railway locomotives, the traction motors, generators, and when you go to the naval frigates, the gas turbines are used to power the propulsion unit. Also, these gas turbines are also used to drive a generator, which is used to provide the electrical supplies to the ship. Even in fact, there are some ships wherein we have a gas turbine driving a generator. This generator will drive again a motor which is going to drive a propeller shaft. Okay. All electrical drive systems are there. Okay. Of course, there are advantages and disadvantages, because once you have this electrical drive systems in a ship, they say that the load at one end is pretty strong, pretty heavy load. So, there can be a situation of stability and instability in a ship. But anyway, so what are the major components of an electrical machine? In this machine here, I am usually referring to a motor. I am not talking about an electrical transformer right now. We will discuss about the transformer later in this class. So, essentially an electrical machine has a stator which actually gives this magnetic field. To give this magnetic field, we need to have the copper conductors of the windings. Of course, they have to be insulated, and then of course, we have the rotors along with its conductors, and rotor body is actually a long shaft on which these conductors are placed. Rotors has to be supported on the bearings, and these bearings are actually put in the enclosure, and then the motor is sealed, of course, to give supply to the rotor. We have either the brushes, slip rings or commutators. So, failure in any of these will eventually lead to the failure of the motor. Even a failure of a motor bearing is also very, very important, okay, to consider. With this, let me just give you a pictorial view of a motor we just opened up in the lab so that you all are able to see. This is how an electrical motor looks in the inside. This is the frame of the motor. This is the stator, okay. And once we give electrical supply to this, there is a magnetic field in this, okay. Because of this magnetic field, there will be flux induced in the rotor. Rotor is nothing but again series of conductors put together. This is each one is a conductor, and these are very soft material because they need to have good magnetic properties. And this is the shaft, rotor shaft, which actually sticks out of the motor, and you can see one bearing at this end, there is another bearing at another end, and this is how it is placed. So, and this rotor here, this diameter here is about 6 inches, but let me tell you, there could be motors, this could be about 6 meters. Now, you could move a truck inside it. I am not kidding, but motors can be that big, but also motors can be very, very small. That depends on the power and so on. Obviously, big motors require a lot of other functions, in the sense because of the eddy current losses, there will be a lot of heat generation. So, you would have seen a motor when it runs, it becomes hot, and if the temperature, if the heat is not dissipated, the temperature is going to rise. Once the temperature rises, it may have many effects. It may heat up the coils, it may degrade the insulation, it may damage the bearings, because the lubrication in the bearings will get baked. Okay, once this lubrication gets baked, there will be hard particles, and if you know hard particles, they are going to scrape the inner surface and the bearings will become rough. So, one leads to another when you have fault developing in an electrical motor. So, you will see that in large electrical motors, they constantly monitor the temperature of the drive end and the non-drive end bearing, because you would have seen at the end of the motors particularly there are. So, this is the rotor. Here actually at the end there is a this is a ventilation blower. So, basically it is going to suck in air, okay, and then pass through this, and then here the motor air is going to come out. So, forced cooling is done to cool the coils. By coils, I mean the rotor coils and the stator coils, cool the bearings. There are class of motors which specify the, because there are motors which run continuously round the clock 24/7, okay, continuously in a plant. Of course, only they take breaks only for maintenance, otherwise they run continuously. There are motors which run for short spans. So, you can imagine if this heat is not dissipated, this temperature is going to build up. Typically, the bearings are maintained to be on the safe side. They should be around 75 degrees Celsius. Okay. And in fact, in some special motors, there are alarms which lets you know that if the bearing temperature is increasing, either the motor shuts down, or we have to have extra cooling unit to cool the motors. So, this could be a serious problem, because once the motor heats up, there may be unequal differential expansion. One conductor may for some reason expand than the other, and this differential expansion will lead to misalignment, will lead to having no concentricity between the rotor and the stator. One will deform more than the other. So, for example, this is a view, because of thermal expansion or some other reason, there is a change in the air gap, because essentially if this is the stator, this is the rotor, this is your air gap. If your air gap changes, the magnetic flux will change, and once this magnetic flux changes, the torque which is responsible for rotating the rotor is going to change. So, many things would happen because excuse me, because of this. Okay. So, for some reason I have a different air gap, flux is going to change, torque is going to change. If torque changes, I will be having a pulsating speed. This was supposed to have an uniform speed, by uniform speed like this, but it may so happen that suddenly there may be this spacing is going to change. Okay. So, this may become like this, and again pull up. So, speed change will occur. And torque changes means your forcing function is no longer steady. Forcing function is changing, the dynamics is going to change. Okay. And over the period, if this goes unnoticed, this is going to be a fatigue load on the machine. Okay. So, you see just one component or aspect, it is if it is left unchanged or unnoticed, it is going to have a dominoes effect, and that is the why we have failures in machines. Okay. Anytime you see a defect initiating, you take remedial measures to remove it, mitigate it. Otherwise, if it goes unchanged, it is going to affect your downstream operations, and that is true for anything. Okay. As I was telling you, this is a motor. Okay, this is an electrical motor about the same as a 900 kilowatt of capacity, and you see this unit here. This is nothing but the blowers wherein the air comes in to cool such a big motor, and this is driving a gearbox actually. And if you see, this is a gear coupling. In a gear coupling, as I was telling you earlier, the coupling allowances for the thermal expansion, and if the motor is fixed and if the gear is fixed, there are bearings on which these rotors, because of thermal expansion, can slide, and other if they do not slide, if they are fixed, they are going to bend, and if they bend, again you know the same problem, the air gaps are going to change, then we will have pulsating forces. So, this is why in large machines we have gear coupling. Gear coupling, basically there are two gears, okay, one over the other, and they will just slide, a little sliding is there. So, that takes care of the thermal expansion. Okay. And this usually again this is used to drive a conveyor system, and you can see the dimensions. There is a my technician standing here, and you can see how big this motor is compared to the person here. This is another view of this motor, which is driving a multi-stage gearbox. In fact, you can see 3 shafts here, 1, 2, 3, and you can see the direction. It is a 90-degree arrangement here. It is a bevel gear arrangement. Power is coming in this direction, and then power is going out in this direction. Okay. And you will see these machines are maintained. The alignment has to be perfect. Otherwise, if there is a misalignment, again the rotor at one end of the motor is going to have an excessive force, and the bearing at one end may get damaged. And this is the view of this motor, another motor which is having a massive reduction gearbox, and this is actually that rotary kiln of that cement plant I was talking about, and you can see the dimension compared to this person. And this motor rotates at 1440 rpm, but this kiln is only rotating at 2 to 3 rpms. So, there is a heavy reduction gearbox as well here. So, critical to a plant is these motors. If the motors die, your plant does not operate. Okay. So, you can imagine your ships will not get unloaded, your cement will not be produced, your steel mill will not work. So, you can have serious effect to everybody. I mean, you can imagine life without electrical motors nowadays, it is just not possible. Okay. I mean, even in small watches to even rocket engines, we have to rely on electrical motors. Okay. And that is a very, very important, I would say, mechanical component, electrical component, any component you call it, it is a very, very important engineering component, okay, which we have to know and which we have to care for. So, with this kind of a background about electrical motors, as you know, now this rotors can have faults, stators can have faults, and the bearings of the motor, obviously they can have faults, and you know how to find out the fault in bearings. Okay. So, what we did in this in our laboratory, okay, we have an motor which is driving a mechanical unit. This is the rotor which is supported on 2 bearings, and we are now concerned with this motor. So, in the we have motors with seeded defects. Okay, by seeded defects I mean there could be faulty rotors typically faulty rotors means, you have seen those rotor conductors like this slots. Okay. So, rotor bar broken is a common mechanical fault. What happens if the rotor bar, one of the rotor bar is broken? Okay. The current which is supposed to flow through this conductor is not going, but to balance the load, the current in the other conductors are going to increase momentarily. So, this will give rise to an unbalanced torque, and because of this torque you will see there will be modulations. Modulations will occur in the current waveform, and from your study of signal processing, modulations in the time domain will give sidebands in the current spectrum. Okay. So, once we see sidebands around the supply frequency, usually typically supply frequency is Fe . By supply frequency, I mean supply frequency to the electrical motor, and typically in our country it is 50 hertz, but now with this many of the motors they use nowadays variable frequency drives, or what is known as VFDs, so that motor can be run at any speed. By the way, for supply frequency in our country is 50 hertz, but in say in USA it is 60 hertz. Okay. And though how do we find out the fault? We can still do our good old vibration monitoring on the motors. I mean, nobody has asked us not to do. We can do vibration monitoring, put an accelerometer on the motor. Okay. I can put accelerometer here. Okay, to do vibration monitoring, and here what will happen, you will see that sometimes I will see peaks at supply frequency and also at twice supply you will see the reason why we are getting this twice supply frequency later on in this class. We can do vibration monitoring, but in this class, since you already know what vibration monitoring is, and all you do is put an vibration sensor close to the bearings of the motor, record the time history, and then do an FFT. But we can also very easily monitor through what is known as the current monitoring. Okay, and in this experiment here, to measure the current, which we are using actually an Hall effect sensor here. If you can see, a sensor is like a clamp on conductor, basically something like this. So this is like a spring loaded thing, and then all you have to do is the conductor actually this is spring loaded, the conductor will actually come here and then you will get a voltage. So, if I am measuring a current I will get a voltage here because of the Hall effect. Okay. I will get a voltage which is proportional to the current, and with time I can be measuring the current. I can be measured. Okay. Usually Hall effect sensors have a sensitivity of maybe 10 millivolt per ampere, etc. The reason we are using Hall effect sensors is because they have high frequency range all the way from maybe 0 or DC to about 500 hertz. I can measure with such Hall effect sensors. Traditionally, we measure current by ammeters, okay. But ammeters have very poor frequency response. They only measure around the 50 hertz supply frequency, and all we get is an RMS indicator, which only gives us the RMS value of the current. Okay. But in the Hall effect sensor, I get the time history. I can record the time, measure and record the time history of the current. Okay, once I get the time history of this current, the entire waveform is available with me. So, with a signal analysis system, I can do the current spectrum analysis and then try to know whether sidebands are there, whether sidebands are not there, and so on. So, this becomes a very convenient way to measure the condition of the electrical motor rather than doing a vibration monitoring. If I do a vibration monitoring, I am not sure that sometimes I will get sidebands around supply frequency. That may not happen. Okay, I may see only the peaks at supply frequencies and twice supply frequency, but that is why the measuring and monitoring current has become a very powerful and convenient technique of monitoring the motor faults. Imagine you are sitting somewhere in a control room wherein an electrical motor is maybe miles away. Okay. All you could do is just lay a current conductor from your motor. Okay. So, you need not go to the motor. Okay. I will tell you why and how. Suppose we have a motor. And you are sitting somewhere in a control room. Obviously, to drive the motor, it requires a supply, and the supply cable is maybe going from here. Okay, I have just drawn one conductor. So, very easily you can measure at this end, measure the current waveform. So, now you can imagine the power of motor current, measurement of motor current. Remotely, motor is elsewhere, motor is underground, motor is over the ground, motor is miles away from you. But as soon as you have access to the supply lead going to the motor, you just measure the current waveform, you will record the current waveform and then do your signal processing to find out the condition of the motor. And this is why motor current signature analysis has become very powerful, and we are not even going close to the motor. If I was to measure the vibration, I have to go at least close to the motor to mount an accelerometer. And that is not required right now, if I am going through this, isn't it? So, in this simulator which we have used in the laboratory, of course, I have an Hall effect sensor, and you can see this Hall effect sensor is connected to a signal analyzer, where we are analyzing the current which has been measured by this, and you can see the time history of the current and the spectrum. Okay. Now, I was just mentioning that what is the source of this twice line frequency in electrical motors. You will see if you multiply these two waveforms, power is nothing but current times the EMF. If I multiply this, the EI cosine 2 pi f t and cosine 2 pi f t minus phase difference, phase between the current and the EMF, I will get this expression. One is the cosine phi plus cosine 2 omega, where omega is 2 pi f. So, one produces the steady torque, which is responsible for the motor, and there is also an unsteady torque at twice supply line, twice the supply line frequency. That is why when you do the vibration measurements or the current measurements, you may sometimes land up with strong 2 times the supply frequency peaks which comes up. Okay. Many times people ask me these questions, why am I in a 50 hertz motor, why am I getting a 100 hertz peak, and this is the reason, this is the mathematical reason behind it, just nothing but multiplication of two trigonometric functions which gives a 2 omega term. Now, let me go back to how this current analysis can be done to find out the rotor faults. Perhaps this equation is not coming clear. I will just write this down here. Okay. This is means if there is a broken rotor bar, this means the frequency in the current spectra is given by this, where this is the K is an integer, S is the slip, P is the pole pair in the motor. Okay. So, in any AC motor, because the slip will occur because there is this difference between the synchronous speed and the rotor speed, pole pairs are there, and this is all functions of the supply frequency. I will get the frequency of the rotor bar given by this expression, and they will actually come up as sidebands in the current spectrum, and this can be calculated. Okay. Now, if a rotor bar, why does it break? Okay. What are the possible reasons? One is thermal stress due to overload in hot spots. Okay. There will be a linear expansion and then will be hot spots, etc. Magnetic stresses created due to electromagnetic forces, unbalanced magnetic pull. I know I just told you, because if the air gap is not maintained, there will be pulsating magnetic field. During a manufacturing process, all of the bars were not having the same stress relieving. So, some could be having residual stress. Because I am rotating, there is a centrifugal forces and thus the stresses. There could be moisture, abrasion by chemicals, contamination, that could lead to the wear and tear of the rotor bar. There are so many loose components in the rotor bar, they are actually fixed in a slot. Few of them could be loose and they could be rattling, and then they will fatigue. So, a good motor takes care of these issues, are not there in a good motor. If you go to the market for the same power, same performance, you will get motors with varying amount of price. That is one of the reasons. The quality, because somebody would have taken care of that, to have good uniform winding, uniform air gap, good bearings, things are not loose. Okay. There is enough provision for cooling, etc. So, this is why motors, these are the possible reasons why these rotor bars can fail. And if this rotor bar, few rotor bars fail, if one goes unnoticed, okay, fine. If 10 goes unnoticed, you will see a lot of them creating such an unbalanced torque that it is going to have effect on the operation of the plant. I have seen many cases, even the supply frequency to the electrical motor creates a lot of problem in the plant. I will tell you how and why. So, for example, if the plant I am supposed to get 50 hertz supply frequency, but because of our power grid supply, I am getting sometimes 49 hertz, sometimes 47 hertz and so on, and sometimes 49.5 etc. So, there is a constant fluctuation of the frequency. So, the motor speed is going to fluctuate. So, in effect, if motor is driving a mechanical unit, it is also going to fluctuate. So, this is going to give rise to fluctuating torque on the. So, there will be a lot of torsional vibrations, which will lead to fatigue failure. I have seen many places where gearboxes rotate a torsion bar. Okay, torsion bar are actually long rigid bars with good amount of rigidity. They have sheared at the 45-degree axis because the torsional shear stress was maximum, and then it failed because of what is the cause? It was the fluctuating speed of the motor. So, there are of course, in modern machines there are many safeguards to prevent that. The system itself will trip. You have seen how the grid failure had a domino effect. One by one the grids fail. If the grids fail, if the power if you do not take up the load, speed frequency is again going to increase. Okay. So, there is always in the power generation place, they have to always maintain balance the load and the production rate. Okay. And so, they have to monitor the 50 hertz. If you have ever been to a power plant, you will see they constantly monitor the supply frequency or the power generation frequency at 50 hertz. If I put in more steam, and there has to be governors to limit it, that it will run at 50 hertz. Otherwise, if I do not govern it, speed will increase, power supply frequency is going to increase. Okay, we all take it for granted, but if you have if you know of a generator, okay, generator is supposed to run at the same constant speed. If I give in more fuel or more steam, whatever to a steam generator, it is going to increase. You would have noticed that in IC engines. If I give in the fuel flow is more, throttle, if you press the throttle more, your car moves faster because the engine is moving faster. But imagine if your generator was going to move faster, your supply frequency is going to change. So, these are things which we cannot take it for granted. I have been to many plants where they say the machine has failed because of the bearing failed or the gearbox failed, but we have found out the cause was actually the supply frequency, which has been changing, and the supply power generating units are actually at fault. So, good power supply to a plant is very, very important. Okay. So, in this example here in the laboratory, what we did is we ran this motor through a VFD drive and not at the 50 hertz power supply, but at 47 hertz in a variable frequency drive with 0.67% slip. And if you see a normal motor, there are hardly any side bands. Okay, these are the side bands which are showing up at 47 hertz. And once we have 3 broken bars, you can see these are the values of the key. These side bands will increase, and you can see it in decibels that the peaks are going to increase, which are the telltale signs that the rotor bar has failed. Okay. There could be cases where the motors could have a static eccentricity. This is the rotor, this is the stator. This has been exaggerated here, and they have an eccentricity A. What are the possible reasons behind this static eccentricity? One is the stator core is not a perfect circle, but oval. Out of tolerances at the end frames that house the bearings. So, bearings themselves are not aligned. Incorrect position of the rotor or the stator at the commissioning stage. Many times the rotors are so heavy that they have to be put right at the site, they have to be installed, and there could be an incorrect installation. 1 foot is at a higher ground than the other, and there is an angular deviation. So, all these lead to the static eccentricity between the rotor and the stator, and because of this eccentricity there will be an air gap variation, and again we will see frequencies coming up in this current spectra because of static eccentricity. Similarly, when it is rotating, I will have a dynamic air gap eccentricity. Okay. The eccentricity is moving with time, you can see how this thing is moving. This could be because the shaft is bent, so it is wobbling. Okay. So, one is the bent rotor shaft, other is the bearing wear, there could be misalignment, there could be mechanical resonance at critical speed, though a good motor designer would have ensured that the operating speed is not at its critical speed or much away from the critical speed. Okay. And once we have these kind of defects in the electrical motors, they all reflect in the current spectra. So, looking at the frequencies in the current spectra, we can find out the faults, and there are equations also here how the supply frequency because of the rotor eccentricity. Again, this is perhaps not visible, I will write it here. Many of these are, this is the number of rotors, and this is an integer. These are all constants depending on the motor. This is a typical value plus minus n d for eccentricity, for dynamic eccentricity. This is about 0.25 or so. Okay. So, these are again some integers. So, researchers have found this formula by which I will see the dominant frequency in the current spectrum due to eccentricity. Okay. I can see this in the spectrum. I will give you another and this could be because of static eccentricity, because of dynamic eccentricity. Okay. Another fault which happens in motor is this bearing faults. Bearing faults also reflect in the motor current. So, the will be nothing but the supply frequency plus minus some number, and these are nothing but the bearing frequencies. You know, if the bearing has an inner race defect, outer race defect, spin, ball spin, etc., these equations can come, these frequencies can be found out here, and these are integers. So, in the supply frequency, you will see side bands about the of the bearing frequencies, and this will be the okay. and this is the supply frequency. Right. So, in effect, if you do faults in electrical motors can be easily detected by current signature analysis. All you have to do is you have to look out for this frequency of the rotor bars, frequency because of eccentricity, frequency because of the bearings, and so on. And we are just in the 3 equations in the previous slides, how they can be estimated. So, that in the current signature analysis they will be actually modulated. So, we have to do an envelope analysis, which we had discussed earlier, or which is what is known as the demodulation. Demodulation of the current to find out these frequencies. And with load, with defect severity, the side bands are going to increase in their magnitude. Okay. Another defects which occurs in motors nowadays, that we are using VFD drives in electrical motors. Because of this VFD drives, VFD drives, there are a lot of high frequencies in the ripples. I have this motor has a bearing, and this is the rotor here. I am just drawing one side. What happens? There will be a current flowing in this conductor, okay, and which gives a voltage. There is a loop, and particularly at the bearing, what happens? And these are very high frequencies, and they could be having voltages about typically about 40 to 70 volts, 40 to 70 volts, and they are going in this loop here. What happens at the bearings? If you will see, there will be a dielectric film. Okay, which is actually an insulator. So, each time the voltage increases, there is actually a spark across this outer race, which is attached to one end, the inner race which is attached to the shaft, and actually the shaft shifts here, the bearing shaft sits here. So, what happens whenever this bearing is sitting, there will be kind of sparking occurring, okay, between the bearing and the shaft. Okay. This spark actually is responsible for eroding the shaft. So, bearing was sitting here, you can see if this goes undetected, particularly in the variable frequency drives, because of this high frequency ripples, okay, they will be sparking on the surface. The shafts become worn out like this, and shafts become weak. So, how do you take care of it is, you have to produce an alternate path to this current by grounding this here, by grounding the shaft. Okay. So, by shaft is here, you have to ground the shaft to the grounding brush, so that the current flows through that route and there is no discharge taking place. Okay. Nowadays, of course, people are using VFD drives and they are coming up with situations where the bearings are having faults, pitting marks, or shafts are failing. Okay. And this we did in our lab is basically we measured just the voltage on the shaft. Okay. Here, of course, we are measuring it, okay, and then we recorded it, voltage across motor shaft and ground. It is a normal case, okay. But when you have the VFD drives at different frequencies, we have seen how that these frequencies are there, and then they discharge and they actually damage. These peaky frequencies, these are as high as 40 to 70 volts, and they damage the motor shafts. So, motor current or motor faults can be detected through these techniques which we discussed, mostly through signature analysis, though you can also do vibration monitoring of electrical motors. And then how do you monitor the condition of transformers? Basically, you would have seen in a transformer essentially is nothing but a core of coil which is there, and this coil is actually kept in a tank full of oil, and this oil is to be maintained for a particular height, and because of again the eddy current losses, etc., this current generates heat has to be dissipated, and that is why these are like fins. You will have seen in many transformers there are tubings, etc., which carry nothing but oil, and this is a tank wherein oil is there. And you would have heard of scenarios where there was a power outage because of a transformer burst. Why did that burst happen? Because the transformer was dry, the maintenance crew had not ensured that the level of the oil which should be there was not there, and that is the reason why transformers burst. So, in our laboratory here, what we are trying is we are trying to measure the vibration of a transformer. Of course, there is no secondary discharge here. We have just done the primary excitation, and this is a very high 100 megawatt transformer which we are trying to analyze. We are measuring the noise here and here through because obviously you cannot go near the transformer. We used a laser beam to measure the vibrations, and here the sound intensity probe. But usually the condition monitoring of transformers is done by monitoring the condition of the oil. We discussed about oil analysis. So, by monitoring the condition of the oil, whether it has its retained physical properties or chemical properties, we can know periodically by taking samples of the transformer oil, whether it has got contaminated with moisture, whether it is time to change change the oil, etc., is how these transformers are taken care of. Of course, again for in electrical switch gears, when there is contact and non-contact, there is a lot of heat generations, and we will discuss in the class on thermography how through thermal analysis or temperature monitoring we can also find out faults in electrical systems. Okay. Thank you.